the middle one. It'll go to a y. Okay, so it'll be y, iy1, but you change this one first, so iy2, right? And then you go iz1, iz2. Well, now you've run out of letters here, so now you change this one, so it'll be like 2x1. So you're back to here, but now it's a 2. 2x1, 2x2, then 2y1, 2y2, and 2z1, 2z2. Okay? So all possible ordered triples. Okay, because you have a Cartesian product of three sets, and there's an example. Now, if you have 3 sets, let's say the number of elements of this one is p, the number of elements of the second set is q, and the number of elements of the third set is r, then the number of elements in the Cartesian product of those 3 sets would be pqr. Yeah, p times q times r. Does that seem reasonable? Yeah? Okay. Now, sometimes you form a Cartesian product using the same set. So say you form a k times Cartesian product of a with a with a, like k times. There's a shorthand for that. You just write it, put 3 bars here. 3 bars means by definition. So you define this as, by definition, as, and you write it a to the k. So this a to the k is just the shorthand for this Cartesian product. Right? So another example, 0.07. So n to the k, now in this case k is 2. So in other words, that's this. So it's n cross n. Now remember what n is, big N, from earlier sessions. Big N is defined as the set of natural numbers. In other words, the counting numbers. In other words, the positive integers. In other words, 1, 2, 3, ... Okay, counting numbers. Little kindergarten kids knows the counting numbers. Right? So you're forming the Cartesian product of n cross n. So what its members, this set. Remember, Cartesian product is a set, right? It's the set of k or e or k or e pair. Trying to remember what the term was. No, forget it. Okay, so in set description type terms, you can write n squared this way. So it's the set of binary pairs, ordered pairs, ij. Ij are integers, right? Well, natural numbers, because n is a natural number, counting number, 1, 2, 3, ... So n squared is the set of ordered pairs of I, j, where I and j belong to, I and j are natural numbers. Okay. Right, now a new topic, a new concept, the notion of function. Very important in pure mathematics. Pure mathematicians, well, they certainly use the word function. They'll often use the word mapping. They'll say they'll use a phrase something like this function maps this value to that value. So a function and a mapping, pretty well same thing. And so here, effectively, like two concepts we'll talk about. So we'll talk about functions for quite a few sessions. Very important concept in pure mathematics. So functions and relations. So just saying by the way, this word function is used so often. I just shorten it to just fn, function, function. Right? Absolutely basic to mathematics. So what is a function? It's well, start off vaguely. It's something that generates an input-output relationship. Like, you can think of it as a kind of black box. Right? Imagine my fist is a black box. Think of it as a function, but you don't know what a function is yet. So this black box, it takes something that comes in, like an input of some sort, like a number or a symbol or whatever. So some input comes in, and then the function, whatever it is, it's some mapper. It looks at what this input is, and depending on what the input is, that will decide what its output will be. So the function is a kind of mapper. It looks at the input and generates an output based on the input. Right? So it's a kind of relationship builder between the input and the output. That's probably a bit vague, but it'll become clearer as we move on. Now, maybe a lot of you have a pretty good idea what a function is, especially from calculus. What is, well, I won't go into that. So, but the use of functions very common in calculus, high school calculus. So probably most of you are fairly familiar with the concept of function. All right. Now, a function in mathematics, unless you're told otherwise, is deterministic. What that means is if you put in the same input each time, you will get, with 100% probability, certainty, you will get the same output. Right? For a given input, you are certain to get the same output. Right? So in that sense, a function is deterministic. Right? The output is determined by the function and the input. Right? So deterministic means the same input gives you the same output. Now, do a little more abstract. So if A is your input, A could be anything, symbol, number, whatever. Something goes in, that's your input. Then your function will map that A into B. So you can look on your function as a kind of mapping. What's it mapping? Well, it's mapping A to B. And what does map mean? Well, to associate, to pair off with. You sort of say you're pairing A with B, or you're connecting A to B. It's a very broad concept, and gets used a lot in pure math. So if you follow me with in the pure math courses, we will be mapping and using functions all the time. Absolutely basic to math, as I keep saying, but it's true. All right. Well, often you can see the first line of the next session. So, it gives an example. So I'll wait till the next session. All right. So think of a function as a mapper. Takes an input and maps it to an output. Takes an input, depending on the function and the value of the input, generates deterministically a given output. And if that output, call that B, then you can say f of A, f of A, hear the thunder? F of A equals B. Right? This is the usual way of writing it. So from this, that's why I put a rectangle around it to show that's important. So if you see this kind of thing and so f is a function, the input's A and the output is B, right? So you're probably used to that from calculus, where A might be X and B might be Y. Y is a function of X. So the y-axis and the x-axis. You draw a graph of the curve y equals fx, some function of x. Right? So, but here's sort of more general example. So I'll just go straight on the next session.